my dear student, Mr. Kitwala from Educatism. I will be with you in physics for Form 5. Now, today we are going to proceed with our discussion on the rotation of rigid boats for our subtopic of the axis theory of rotating of the boats. This is our second session for this subtopic. So welcome here to proceed with our discussion. And before we proceed with our discussion here, we are supposed to remember where we ended on the last session. On the last session, we tried to see the concept of the parallel axis theorem. We tried to get some concept and the law. How can we state the moment? How can we state the parallel axis theories? And we say that this law say that the moment of inertia through any axis of a rigid body is equal to the summation of the moment of inertia through the center. Then we add it by the product of the mass of the rigid body, we times it by the perpendicular distance through the parallel axis. That is what we try to see. And after there, we looked at how can we derive that formula? How can we prove that the moment of inertia must be equal to the moment of inertia through the center? We add it by the mass times the square distance. This is what we tried to see on our last session. So on our today discussion here, we are going to see how this theorem can be applicable. How can we apply this theorem? Where it is can be applicable. This is what we are going to see on our discussion here. The application of the parallel axis theorems. So consider our statement here say that parallel axis theorems is used to determine the moment of inertia of the homogeneous rigid boats with different geometries. So this moment of this parallel axis theorem, it is very, very important because it is used to determine the moment of inertia for a homogeneous rigid body with the different geometry. This is what we are going to observe here with a different geometry. We are going to see that if we have how can we take this parallel axis and apply either for the cylinder or for the uniform load or for the sphere? That is what we are going to try to demonstrate. So don't miss it. Let us continue following here so that you can learn more about this concept. So as we try to see that the different geometries is like example those cylindrical shell. We are going to see how it is applicable for the cylindrical shell and also how it is applicable for the uniform load. How can we determine at the moment of inertia using with it through the uniform solid sphere, also the hollow cylinder, and also the rectangular plate. That is what we are going to try to observe or to demonstrate here. So my lovely student, as we try, we can say that for a uniform load of mass M and also the length L, consider the figure number 4.4 as we tried to see on our past lecture. We tried to see the figure number 4.4 that explain about the uniform load, how the uniform load looked like, how the uniform load can rotate about an axis through an axis. That is what we tried to see on that figure. So the moment of inertia about an axis through one end is given by this one. As we know that through an axis, we can get the moment of inertia by taking the moment of inertia through the center. Then we add by the mass of ends, and we times it by the square. But this square represents their distance. But now you have to remember that we focus on our uniform load. If we focus on our uniform load, now we are supposed to know how can we get the moment of inertia through the center for the uniform load. But we know that if the uniform load rotate at one end, we could say that their distance here must be equals to L divided by 2. Then we can say that instead of writing D, we should represent equals to L divided by 2 here. So after this one, let us go and substitute here. And after substituting, let us go and look for the moment of inertia through the center for the uniform load, kwamba tuashumu ile ilikuwa ina rotate through kutoka kwenye one end mpaka kwenye center. Sasa moment of inertia aliyepo kwenye center pale tunamjua kabisa, tulijaribu ku demonstrate for the uniform load which is equal to 1/12 times ml square. That is where m represent the mass of the rigged body and also L represent the length of the rigged body between the two parallel axes, where as we tried to see. So if we substitute the moment of inertia through the center, which is equal to 1/12 ml square, and also D equals to L divided by 2, then we should obtain that moment of inertia overall should be equals to 1/12 ml square. We add by mass, then we times it by L square divided by 4. If we simplify this one, because here is L square divided by 4. If we find the LCM here, we should obtain that. If we simplify, we should obtain moment of inertia through the uniform load for the parallel axis must be equals to 1/3 ml square. So this should be our formula of obtaining the moment of inertia. So after this one, let us say that any for a solid sphere of mass m and radius r, the moment of inertia about an axis tangential for the surface is given by this one. So this should be for the uniform load. Now we are going to see about the sphere. How can we get the moment of inertia? That is what we are going to try to look at how this one it is applicable. So for here, the key point that we have noted on our mind is that the moment of inertia, the parallel axis theorem is very, very applicable on demonstrating or on delivering the moment of inertia for the different geometry, like the uniform load that we tried to get, which is equal to 1/3 ml square, where m represented the mass of the uniform load and this L represented their length square. So after this one, my dear student, as I said that we are going to see for the solid sphere of mass m. Now, how can we get the moment of inertia for the solid sphere? So for the solid sphere that involve containing the mass m and also the radius I about an axis tangential to the surface. Now it can be demonstrated using the law of the moment, the law of the parallel axis, by saying that the moment of inertia of a rigged body must be equals to the moment of inertia through the center. Then we add by the mass times the square distance, as we see which the distance is perpendicular to the parallel axis. So if we substitute the moment of inertia through the center, which is equal for the solid sphere, we try to demonstrate on our past figure that equals to 2 divided by 5 mr square. Now we should substitute, instead of writing Ig, which is the moment of inertia through the center, we should substitute is equal to 2 divided by 5 mr square. While this one, we should imagine that the distance should be equal to the radius. Kwa ile distance ambayo ita-act kwenye ile sphere between the two parallel axes must be equals to the radius, as we try to see. So if we simplify this one, my dear students here, now if we try to simplify, we should obtain that moment of inertia for the solid sphere for the parallel axis of for the parallel axis theorem must be equals to 7 divided by 5 mr square. Kwa hiyo ndio formula yetu, hii ndio matumizi ya parallel axis theorem kwa ajili ya kudemonstrate moment of inertia ya ile solid sphere. Kwa tutapata ni sasa na 7 divided by 5 mr square. How this one it is obtained? This, my dear student, is obtained by finding the relation. Let us put over 1, or we can factor out this mr square because it is common. If we can factor out, we should remain with mr square bracket 2 over 5 we add by 1. Now, if we simplify the fraction, the equation of the fraction, as we know that we have been taught when we was at the primary level, we know how we can solve the fractional questions, how we can add. So if we add here, we should obtain that moment of inertia must be equals to the 7 divided by 5, then we times it by mr square.